Hello everybody, it's Benji again. How's everybody doing? Welcome to the second episode of our Gaming Scientifically series. As usual, here are the timestamps if you are impatient. Last episode, we talked about how to scientifically combo interrupt. And it's not about reflexes. A little spoiler, Dream, the Minecraft YouTuber, explained how he consistently hit perfect frame jumps in the MCC Parker games. And what he does is basically the same as what I talked about in this combo interruption video. Great minds think alike. So if you haven't watched it, I'll link the video to the top right now. So go check it out and subscribe to Dream. In today's video, I'm going to teach you the basics of all Gacha/lootbox game modes. The underlying thing is just probability, really. So you can also apply this to any other chance-based events as well, like what to expect when opening a solo raid vault, how to play a level 1 puppet. Well, disclaimer, parts of this video is very math heavy, so if you just want a formula, jump to. But if you're interested in the derivations, stay, and I'm sure this will help you a lot. First of all, let me show you two chests, and just think for a second, which chest gives you better chance at winning a character? On the one hand, we have a total of about 8% chance to get Beast Boy and Raven, both at 3 stars. On the other hand, we have about 8.5, 4.2, 2.2, and 1% to get 50, 75, 100, and 200 shards. So which one is the better chest? If you guess the moral support chest, which is the top one, congrats, you are correct. You are a genius.
Thank you.
But ask yourself this, by how much? Well, let's first zoom in on the moral support chest. Assuming you are fine with getting both Raven and Beast Boy, what's the probability of not getting any legendaries twice in a row? It's the same as flipping a coin and getting 2 heads in a row, just the probability of flipping head squared. Okay, what about 3 times in a row? That's just the probability cubed. You might be wondering, we want at least 1 legendary. Why are we calculating the probability of getting nothing? That is a good question. Let me introduce you to the concept of complement, although I'm sure some of you are already familiar with this. Say this rectangle here represents the total possibilities of 10 pull. So that contains the probability of getting 0 to 10 legendaries. And this yellow circle here represents the probability of getting 0 legendaries. What does that mean? That means outside of this circle, the other parts of this blue rectangle is the possibility of getting 1 to 10 legendaries. So getting at least 1 legendary. Now, if we want the probability of getting at least 1 legendary drop from this chest, we only need to calculate the complement of dropping nothing. That is 100% minus 7.217% to the 10th power. And that is equal to about 92.8 to the 10th power, so about 47%. Now, what's the opposite? What's the complement of that? What is the probability of getting at least 1 legendary? Isn't it just 1 minus 47%? And that is equal to 53%. So the chances on this chest is pretty good. You have 53% chance to get at least 1 legendary in 1 temple. What about the other chest? The other chest is way more annoying to calculate because it does not give whole character, it gives shards. What can we do? What we can do is keep going down the get the complement path. What we are interested in is the probability of getting at least 1 legendary. And how many shards do you need to unlock a 3-star legendary? 200. So we want the probability of getting at least 200 shards in 10 pulls. But there are thousands or like infinite combinations for getting 200 plus shards. How are we going to calculate it? Remember the complements method. To calculate the probability of getting at least 200 shards, we only need to calculate the probability of getting at most 200 shards. Or like less than 200 shards, and that is much more doable because there is only a handful of combinations. Let's list them out. You can get 0 shards where you drop no shards, 50 shards where you have 1 50 shard drop, 75 shards, 1 75 shard drop, and 100 shards, 125 shards, 150 shards, 175 shards. For each of them, you have a bunch of combinations. Let's calculate all of these subchances or scenarios and sum them up to get the total chance of getting less than 200 shards. For convenience, let's assume the drop rate is 2% for 200, 4% for 100, 6% for 75, and 10% for 50 shards. Let's focus on the first scenario, the probability of getting 0 shard. It is the same as how we calculated for the moral support chest. Again, we can calculate the probability of getting nothing drop, so no shard, 0 shard, in a single pull. That is just 1 minus 2%, minus 4%, minus 6%, minus 10%, which is 78%. And that is the probability of dropping 0 shards. Thus, not getting any shards in 10 pulls is just this probability, 78% to the 10th power, which is about 8%. Now, we can just do the same for the rest and add them together and take the complement and bam, you got your answer. It's that easy, right? Right? Well, you might have noticed that I only taught you how to calculate the dropping nothing in 10 poles, but I haven't taught you anything about dropping exactly one thing in 10 pole. If you want to skip the explanation, the derivation, because the next portion is very, very math heavy, you can skip to... I'm sure you don't want to do math when you're off work or off school. Well, you know things are serious when you see a scratchbook. So let's say there is a new chest and the NetherRealm Studio is being extra generous. There is a 40% chance to get Killer Frost. And this is every pull. You have 40% chance to get Killer Frost. And what we are interested in is if we do 2 pulls, what is the probability of getting 1 Killer Frost and 1 garbage? Let's list things out. So in the first scenario number 1, on the first pull, we have Killer Frost. And what's the probability of that? That is just 40%. And on the second pull, we get a garbage. And what's the probability of that? That is just 1 minus 40%, which is 60%. And what's the total probability? That is 40% times 60%, which is 24%. But wait, there's a second scenario. On the first pull, we get a garbage, and that is 60%. On the second pull, we get Killer Frost. That is 40%. So it's again 40% times 60%, which is another 24%. So what is the total probability for you to get Killer Frost? That is just 24% plus 24%, which is 48%. And I'm sure you're smart enough to see that the probability, the expression here are the same. So basically, we have the probability of one thing, and then you can just times 2 to get the total percentage. All right, following the same logic, say we still have 40% chance to get Killer Frost, and now we are doing a 10 pull. What is the probability that inside this 10 pull, we get 1 Killer Frost and 9 garbage? That is, let's say, in scenario number 1, we get Killer Frost on the first pull, yay! And then second to 10th, we get nothing. The probability of the first scenario is 40%. The probability of the subsequent 8 scenarios are 60%, and there are 8 of them. So the total probability in this scenario is 40% times 60%, but remember the 9 here to the 9th power. And the total probability is... Okay, but that's just scenario number 1. What about scenario number 2? Now we have 10 positions, right? 10 positions. Right now, our Killer Frost will be happening on the second position. And then how many possible sequences or how many possible places can Killer Frost occur? That's just in every subsequent positions. And the total number of scenarios is 10, which is equal to the 10 pull we're doing. So the total probability is 40% times 60% to the 9th power and then times 10. Neat. And the total probability is... So back to reality, the probability of getting exactly 150 shard drop in 10 pull is just the probability of one scenario where you drop the 50 shards on your first pull and then dropping nothing on the subsequent 9 pulls, times 10. The same thing goes with the 75 shard drop. And we can get the following expression. For the 50 shard drop, it is 10% times 78% to the 9th power, and the whole thing times 10. For the 75 shard drop, it is 6% times 78% to the 9th power, and the whole thing times 10. And the final answer is 11% for 50 shards and 6% for 75 shards. Okay, so that's 2 more solved. The next one is 100 shards. You can get 100 shard drop, which we can calculate with the same method. However, what about the 2 times 50 shard drop? How do we calculate that? Again, the derivation is pretty long. If you want to skip that, you can skip to this time I put on the screen right here. But if you survive the last derivation, the next one is 3 times as long. Yay! If we want to figure this out, we must separate the probability of one scenario and the number of scenarios. We can't quite do the same as what we did for the last 2 examples. Trust me, I wasted 5 hours of my Saturday. And it led to nothing. But feel free to try it yourselves as you might be smarter than me. Let's first figure out the probability for one single scenario. Imagine the 40% chance Killer Frost chest again. What is the probability of getting 1 Killer Frost on the first pull, another Killer Frost on the second pull, and from the 3rd pull to the 10th pull, they're all garbage? It is just 40% times 40% times 60% times 60% times 60% and times 60% 8 times. I'm sure that you have noticed that the general formula for this scenario is just the probability of getting killer frost to the 8th power, and A here is just the number of times you want to get killer frost, or the number of times you get killer frost, times the probability of you not getting killer frost to the bth power, with B being the number of times you don't get killer frost. That's one part of the puzzle solved. We now know the probability of one scenario. Let's next figure out how many total scenarios there are. Assume you have 5 boxes to fill, and I will give you 5 cards. There are 3 A's, 1 B, and 1 C. How many ways can you fill the cards into the boxes? You can fit A1 into box 1, A2 into box 2, A3 into box 3. However, you can also fit A2 into box 1, A1 into box 2, A3 into box 3, and you can fit A3 into box 1 and blah 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 blah. It's just too much. So what about let's consider this. Let's assume that they are all different. So instead of 3 A's, 1 B, and 1 C, you have A, B, C, D, E to fill in these 5 boxes. In the first box, you can have 5 choices. You can fill either A or B or C or D or E. But after that, in the second box, you can only have 4 choices. If you filled A in the first box, then you have B, C, D, E. And the same goes with the rest of the boxes. So on the third box, you have 3 choices. On the fourth box, you have 2 choices. And on the last box, you only have 1 choice. What is the total number of possibilities or combinations that you can have to fill these boxes? That is just 5 times 4 times 3 times 2 times 1, which in mathematics, it is called 5 factorial. It just means whatever that number is, you just keep multiplying it until 1. Okay, let's pin this because we're going to use this later. Okay, onto the notebook. So how about this? We are doing 5 polls, and in those 5 polls, we want 3 of them the same. And let's say this is like 3 A's. And then the other 2, we don't care. And they're different, they're not the same, and we don't care about that for now. So we have 5 polls. And then let's see, how can we fit the 3 A's onto these 5 polls? Let's start with 1. When I say 1, that's like the first A. And then when I say 2, that's the second A. So the first scenario, we can have the first A on the first, second A on the second, and the third A on the third. And the rest, we don't care. And then on to the second scenario, the first A is still in the first spot, and then we still have 2 on the second spot, and then 3 on the fourth spot. And we can keep writing and get this. But we can also have 3 on the second spot, and then 2 on the third spot. And if we keep writing, it'll look like that. And that's all of the possibilities or the combinations when the first A happened on the first spot. And then there's also another A on the second spot. Well, let's move on to here. 1, 2, 3, 4, 5. The first spot still has an A, but the second A appearance is on the third spot. And then we can keep writing, keep trying the possibilities. 1, the first A is there, the second A over here. Keep in mind, although I'm using like numbers, different numbers, they're all just A's. Let's move on to the next. 1, 2, 3, 4, 5. 1, 2, 3. 1, 3, and 2. This seems like to be all of the possible combination when you have 1 on the first spot. I've like emphasized many times, although I use 1, 2, 3, they're all just A's. And let's just think for a while, like what would happen if instead of the first spot being 1, the first spot is 2. You would essentially have this thing over here again, like with 2, 1, 3, 2, 1, 3, 2, 1, 3, blah, 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 blah. That's going to have the same number of combinations as this one. What about 3 being first? You will have another set that's like that. And remember the thing we pinned? If we have 5 boxes and we're trying to fill 5 different cards in it, we have 5 factorial ways to fill it. Remember I said, although I use 1, 2, and 3, they're all just A's? That means we have a bunch of repeats. These 2 groups here are exactly identical to the first group that we've listed out fully. And thus, the real number of combinations we have is 5 factorial over 3. Oh but wait a minute. What about here? Let's divide group 1 into 3 segments. Because 1, 2, and 3 are all A's, so we can see in each segment there are a bunch of repeats as well. For example, here 1, 2, 3 is the same as 1, 3, and 2. It's essentially just A appearing at the first, the fourth, and the fifth place. These 2 are the same. These 2 are the same. It's 3 A's occurring at the first, third, fourth, first, third, fourth, first, third, fifth, first, third, fifth. And moving back to the first segment, we see that the first one is the same as the fourth one. The second one is the same as the fifth, and the third one is the same as the sixth. You see that there is half of them in each segment that are repeating. That means we can divide another 2 onto our total combinations. Remember, factorial is whatever that number is, and you just multiply it until 1. So we can write a little times 1 on the denominator, and the whole thing turns into 5 factorial over 3 factorial. And that we can convert into a general formula. We are doing 5 poles, and with 3 of them being the same, the number of combinations is 5 factorial over 3 factorial. So if we have m poles, and n of them are the same, that means we can have m factorial over n factorial combinations. What if we add something? Now we consider 6 poles, and inside that 6 poles, we want 3 of them to be the same, to be A. And then additionally, we want 2 of them to be the same as well, but this time it's B. For 6 poles and then getting 3 identical cards, the total number of combinations is just 6 factorial over 3 factorial. But what about the 2 identical card Bs? Let's list out the possibilities again. We have 6 poles, and then let's just say in the first scenario, we get the 3 A's on the first to third slot. So that leaves us with the 4th to 6th slot. And now we just have to fill the 2 card Bs into these 3 slots. And you can think of it this way. Because the 1st to 3rd slot is already fixed, they are just A's. We can think of this as you do 3 poles and then 2 of them are the same, which we already have a general formula for that, which is 3 factorial over 2 factorial. And this big scenario here, where we have 3 A's in the 1st to 3rd pole, is just equivalent to one of the scenarios we have over here. So back to this page, the 2 factorial here is for removing repeats from the 3 factorial. And the 3 factorial is the number of possibilities that exists inside of every single possibilities of that 6 factorial over 3 factorial. Thus, to further remove repeats, we can just simply divide the 6 factorial over 3 factorial by 2 factorial. Phew, you made it. Now, we can just write this as a general formula. If you want to do m poles, and you want to get n1 of A, n2 of B, n3 of C, n4 of D, and blah 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 blah. The total number of combinations is just m factorial over n1 factorial times n2 factorial times n3 factorial times n4 factorials times blah 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 blah. This is the total number of scenarios. And remember, from the Killer Frost example, we have said that if you want A copies of Killer Frost and B copies of nothing, the total probability is just the probability of getting Killer Frost to the 8th power and the probability of not getting Killer Frost to the Bth power. We can expand that and say in m poles, if you want n1 copies of A, n2 copies of B, n3 copies of C, and blah 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 blah, the total probability is just the probability of getting A to the n1th power times the probability of getting B to the n2th power times the probability of getting C to the n3th power, and blah 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 blah. And now, not only do we have the total number of combinations or scenarios, we also have the probability of one singular scenario. And we can finally just combine them together to get the final formula. This formula is also known as the multinomial distribution function. Now that we have the general formula, we can just plug the rest of the shard combinations into the calculator and get the results. And in the end, the sum is about 55%, which means in a 10 pole, we have 55% chance to get less than 200 shards. And if we get the complement of that, which is 100% minus 55%, which is 45%, that is the probability of getting at least 200 shards. So it is 45% to get at least one legendary character in 10 poles. Remember the probability to get at least one legendary character in the other chest? That was 53%. So there you go, we have a winner. And keep in mind that for this shard chest, I have rounded up the shard probability. So in reality, it's actually worse. Now, I know nothing about coding, so I let ChatGPT to write a code for me. This is the prompt that I gave, and I'll leave a link in the description for you to read the code yourself. Or you can download it and you can even run it in ChatGPT if you want. After I input the real drop rates into the code, it gave me a 27%. So that is significantly worse. Okay, that is all from me today. I hope you survived all of that. It took me so long to edit this video, but I hope it helps. Because with this knowledge, you can easily calculate basically everything probability related in this game.